All right, wait for it. I'll be there soon. I'm running to the front of the classroom. Here I go. All right, let me do some demonstrations here now. Sadly, there's two demonstrations that I can't do, but I'm going to at least talk about them. We can joke about it or whatever, right? The first demonstration is the liter, okay? Here I have a liter of water. Now remember, there are 1,000 of these in a cubic meter. 1,000 of them, okay? This is what you use in chemistry, and here I have a cube, okay? A very small cube, and what I'm going to do is I'm going to pour this into there, and when it's full, I'm going to empty it out. I've got a little bin here, right, that I can empty it into. And my question to you is, how many of these am I going to fill before I've emptied that? So I'm going to pour it. When it gets full, I'm going to pour it out. I'm going to keep pouring out of this, and we're going to count how many times I have to empty this. Okay? So just pause for a little. Pause the video and make a prediction. I need you to predict. You're not pausing. You got to pause. All right. Here we go. I am pouring. I begin to pour. Here we go. I begin to pour. Suddenly the cube starts to look big, doesn't it, right? Whoa. Whoa. Did any of you predict that it would fill the cube exactly once? Filled it exactly once. And that's because that's a liter. This thing measures 10 centimeters by 10 by 10. Well, 10 by 10 by 10 is 1,000 cubic centimeters, and so therefore this is also a liter. Okay? When you buy shampoo, though, it's in nice, tall, narrow bottles, so it looks like a lot of volume. You never buy it in these square bottles like that. All right, ladies and gentlemen. All right, there's nobody here. Okay, my next demonstration is density, and the concept of density, okay, the mass divided by the volume, is the idea of how much stuff there is in a given space. You keep the space the same, right? So I've got these two boxes here, okay, with markedly different densities. And what I usually do is I hand one of these boxes. This is, by the way, an empty box. Okay, I hand this to a kid. I go, here, can you take these, right? And I hand this to him, right? And they'll go, oh, I'm gonna put it down. Then I'll hand the second box, right? And I'll try not to indicate that this one's full of sand, right? I'll hand that to him, and usually the box just kind of falls down on the ground because you don't anticipate it. Was that a good demonstration? Okay. And nobody here. I just wanted to talk about what a good demonstration that was. Okay. All right. The second one, I went to get this out of the closet, and this is why I don't drink soda pop very often. The soda, if you get regular Coca-Cola and Diet Coca-Cola, okay, so you can do this demonstration. Get a can of regular Coca-Cola and a can of Diet Coca-Cola and put them in the bathtub. Shake all the air bubbles out of them, or put them in a big pot of water. Okay. One of them floats and one of them sinks. Okay. My cans of Coca-Cola had eaten through the aluminum. They had dissolved the aluminum and made a mess in my cabinet. Okay, so that one's not going to happen. Okay, but I can do this other one. Okay, so I'm going to do this, and I also am going to post another video. So you see the video posted about the phenomenon in Africa. In Africa, they've got a name for this, but I can't remember the name. But it'll be on that video. I'm going to take this candle and light it. And that candle is there happily consuming oxygen, right? And what I'm going to do here is, I guess, dim the lights a little bit. Does that work? There we go. All right. I'll dim the lights. Maybe it'll. Okay. Oh, that's a lot better. Okay, so you can see that. And the next thing I'm going to do is I'm going to take this big beaker here, and I'm going to pour some. That's baking soda in there. I'm going to pour some vinegar in there. Okay. And we know that that's going to generate, that's a lot of, all those bubbles have CO2 in them, right? Okay, so the chemists in them just balance that equation, right? But here's the thing you got to know, is that the density of air is mostly nitrogen, right? And it's diatomic, so it's 2 14s, it's roughly 28 grams per mole, right? But carbon dioxide is much more dense, because it's what? Well, carbon and 2 oxygen, oxygen 16, okay? So that's 32, and then plus 12, that's 44, so it's more dense. Okay, so this carbon dioxide is actually, since it's the same as a clear odorless gas, it's just accumulating in there, right? And this is the danger with this, okay? Now what I'm going to do is I'm going to pour the gas, but I'm not going to pour the liquid onto that flame. So just watch the flame. There we go. Okay, notice the liquid hasn't moved. I put the flame out with the carbon dioxide, and I literally poured it out. You can't see it because it's the same color as the air. In fact, you might have seen maybe a ripple if you shone light through it. You would have seen a ripple. All right. Okay. This happens in Africa, and I'll send the video. What happens is volcanic features, and this can happen in America too. Okay. Volcanic features can cause carbon dioxide to come out of the ground. It can pool in places like valleys or low areas. And if you try to walk through that area, there's no oxygen. Carbon dioxide is also, I think, lethal. Okay, if you breathe carbon dioxide, you can get carbon dioxide poisoning. All right, what do we have? We've got, the level tube. The level tube is always a good thing, right? So when we talk about the hydrostatic pressure, right, that pressure is rho GH. Notice that the only dimension that it deals with is the height, how far you are below the limit. Okay? So what I'm going to do is I'm going to pour some water in here. This is just ordinary water. Now water is blue, right? This is blue water. It might be water with blue food color, right? Notice that the giant tube to my right, to your left, okay? This tube right here is big. There's a lot more water in here, but that water is not able to force this water any higher up in this pipe, or any higher in this, or any higher in that pipe, okay? The level stays the same. Let's have some applause for that. Don't touch your face. All right, so this level, all it depends on, the pressure at the bottom here just depends on how far we are below that surface, okay? It doesn't depend on any other geometry like that. It's simply the height, okay? Because imagine if it, like, let's say that this water level, like there's more pressure down here than there was here, okay? Then this water would force water this way, water would come off of here. We could run it through the pipe, through a little paddle wheel, and we could generate electricity. We'd have a perpetual motion machine, and that just can't happen. And that's what the first law of thermodynamics. Now let me pour a little water out of this. And let me just show you another phenomenon, okay? The other phenomenon is that water will seek its own level. Now, I don't know if you can see this, I hope you can. But see how it's, like there's one level here, like literally the water levels itself. Now there is some discrepancy, right? There is some capillary action, so it's going to climb maybe a little higher in the tube, okay? But it's pretty much seeking its own level, which is kind of a cool thing. This is why we use fluids in levels, okay? Usually we use like air bubble. There it is, right? So let me show you the final demonstration. I'm going to pour blue stuff all over the top. Okay, my final demonstration is the hillbilly level. Okay, actually it's not my final demonstration. I've got another demonstration. I have to do a trigger warning before I do that. Okay, here is, I call this the hillbilly level. Now, that's what it's called. I don't really want to call it that because I've actually used the hillbilly level. Okay, what I've done is I've set up a siphon with this. Okay, I got the water into this tube, and you could do that without putting it in your mouth. So I did that. And then what will happen is when I put this guy up here, it will, as long as there's not too big a height difference here, as long as it's not more than 32 feet, then this water will it's actually filling that lower thing. And you can see that it's now, like there's less water in there than this one. Right? And I can lift this up, I can make this not level. It's going down pretty fast, you can see that. So water's flowing into that lower one. This is called a siphon, okay? I've just shown you how to steal gasoline out of a car. But don't ever do that. In fact, don't ever start a siphon on a car with your mouth. Okay? People die doing it because the petroleum can coat your lungs and kill you. Okay? But look at these levels. This water will stop flowing only when that level is the same as this level. Okay? So I can put this, if I'm leveling, say, a foundation or something like that, if I'm digging and putting a retaining wall or something like that, and I need to level a foundation, I can mark where it is on this and mark where it is on this. And I can put this here and this there. And this pipe can go anywhere. It can go up and over things. It can go over a wall. Okay? The water is going to stop flowing only when this level is the same as this. Okay? Nobody uses this anymore, by the way. There's a really cool laser level that can construction workers use. It's much easier to use than this, but this is cheaper. You can do this with a garden hose and 2-gallon buckets. Okay? I'm going to put this guy up on something. I'm going to put it up on something on a box of matches. Okay? Let's put this guy on a box of matches. Let's see what happens to the level of the water. All right, I'm going to put that. We can just watch that. Okay. Now, the next thing, this next demonstration that we've got is going to be so astonishing. It's just a trigger warning. Get yourself in kind of a safe place here. I don't want anybody getting injured at home watching these demonstrations like, oh my gosh, this is so amazing. Okay, just brace yourself for this, okay? The final thing is the idea of hydrostatic pressure. Okay, if I've got a container like this, if I say it's full, right, this one's not full, but if I drill a hole right here, there's not very much pressure. If I drill one here, there's more, and then down here, there's going to be a lot of pressure, okay? Can I demonstrate this? I don't know. All right, here we go. All right, you ready for this? Here it is. I must warn you, this is very dramatic. Can you even see that? There. Can you see the water? So it's shooting out really fast there. It's kind of dribbling out of this one and kind of moderate there. Right? All right. Yeah. Wow. That is like the worst demonstration ever. I was just trying to play it up. There. You can kind of see those streams of water. Now it's not coming out of here because the water level's gotten down. Ladies and gentlemen, those are my demonstrations. I will post that video. It's a super cool video about the volcanoes in Africa. And all right, thank you for watching these really boring videos. You must be here. Oh wait, wait. You haven't seen this. The levels. We could wait a long time here. I think I'm just going to stop. But this water will stop flowing when that level is the same as that. Okay. By the way, if it ever flowed beyond that, maybe let's say this one higher and this one lower, right? That would be perpetual motion. You could harvest energy by letting it flow over the top. All right, I'm going to stop talking because you've got so much physics to do.